Yo, welcome back. Syndicate Laboratory presents the NucleoGenesis project. My name is Dr. James Utley. If you don't know, I'm your resident codebreaker data scraper, and I'm here to tell you about this framework, my project that I've been working on. All right, so here we go. NucleoGenesis, as a refresher, is a temporal framework for eukaryotic nuclear blueprint archival and reconstruction. So what that means is basically taking a nucleus, building a digital file or a nuclear blueprint manifest, and then being able to keep that manifest up to date. So there, once you get to a state in the future in the future of synthetic biology, that then you could reconstruct this nucleus, and voila. Anyway, let's get to we're if you haven't been watching, there's two other parts. There's a primer, which kind of goes over it very basically, and then secondly, there is a cringeworthy abstract presentation, which is the video before this. But now we're going to move into part one, which is the foundational paradigm. So, all right, so the nucleogenesis project, right? So, foundational paradigm is a temporal decoupling of the acquisition and reconstruction. So, let's get into it. Previous attempts at the nuclear reconstruction from archival biological material has failed, not due to technological insufficiency, but due to a category error. The implicit assumption that all nuclear information must be preserved simultaneously and recovered in reverse chronological order. This assumption conflated two fundamental distinct informational domains within the nucleus, those that are chemically persistent and those that are biophysically emergent. So at the moment, biological sample collection, the nucleus contains both sequence encoding information and the structure encoded information. So both sets of information. The genomic sequence and DNA methylation are encoded in a covalent chemical bond and exhibit low Shannon entropy relative to their information density. Once specified, they are highly compressible, stable under dried out desiccation. It's a crazy word. And recoverable via a dried blood spot matrices with minimal information loss, right? So that's an assumption. There's some assumptions there. And that is, so in contrast, the chromatin architecture, including three-dimensional genomic context, that is nucleosome positioning, chromatin accessibility, and the histostate. It is emergent. That is in the emergent high entropy system that depends on intact nuclear scaffolding, the biophysical forces, and really the cellular context, like what cell is it. But upon lysing and dehydration, this information is irreversibly destroyed. All right, so let's back up a little bit. So what that means is we have basically two things that we're looking at, which is the stuff that's chemically persistent that we already know of, right? And then we have the stuff that's biophysically emergent, which is the stuff that we want to know. So what that means is that when in a dried blood spot card, when it starts to dry out and lyse the cells, right, that the information on the biophysically emergent side, right? So that means like the chromatin architecture, the genomic contrast, contacts, the nucleosome positioning, and really anything like about the histone state. That is, since it's a high entropy system, it is then destroyed, right? Now, formally, the information context of a nucleus can be decomposed as, you can see there. But critically, the Shannon entropy of chromatin state far exceeds that of the genomic sequence. While sequence information defines a constrained finite solution space, chromatin organization represents a dynamic configuration drawn from vastly larger sets of permissible states. Consequently, chromatin architecture cannot be recovered from the sequence alone, nor can it be meaningfully inferred after nuclear disassembly. So that's like super important part. Attempts to do so implicitly treat nuclear reconstruction as a process of temporal reversal is an assumption that is physically invalid. Just can't be done. So nucleogenesis resolves that limitation through the principle of temporal decoupling. Rather than attempting to preserve all nuclear information indefinitely, the system separates information acquisition according to time and physical survivability. So you see, that's the purpose of the temporal, right? High entropy, structure-dependent nuclear features are captured contemporaneously, such a tough word, at our T0 using the fresh cell, our fresh cell testing or fresh cell assay. While low entropy, chemically stable features are archived in the dried blood spot format for an indefinite future access. So you test the stuff now that has it's high entropy, needs to be tested before it degrades. Then you have an archival mechanism, which is a dried blood spot. So then you're testing that in the future, or you're correlating that mechanism or how fast it degrades or what time it actually is degrading against the fresh sample. So anyway, that's a temporal decoupling. All right. So under this framework, nuclear reconstruction is not defined as a reversal of biological degradation, but as a problem of constraint satisfaction. So just solving the problem. Like we know everything is going to degrade, but archival sequence and methylation data provide an immutable boundary conditions while contemporaneously captured chromatin priors construction constrain the permissible solution space of the nuclear organization, right? So reconstruction proceeds by identifying a nuclear configuration constant with both constraint sets rather than attempting to recreate the original nucleus from atom to atom. So it's a little tough. I know it's a little abstract, but this reframing transforms nuclear reconstruction from an impossible act of biological preservation, so just trying to keep it in one state, into a solvable information theoretical problem. So what you're doing is instead of trying to like keep everything in one static state to then use it or reconstruct it or see it in the future, what you do is you just reconstruct the parts that can be or preserve the parts that are known to be easily to be preserved, and then reconstruct everything else via assumptions and predictions. Okay, so synthetic reconstruction of the nuclear state without requiring long-term preservation or fragile chromatin structures. So anyway, I'll just go over next is the biological rationale. The molecular basis for this partitioning arises from the fundamental difference of chemical and physical stabilities of the molecules that encode nuclear information. So that's like a real like a framework type statement here. The molecular basis for this partitioning arises from the fundamental difference between chemical and physical stabilities in the molecules that encode nuclear information. While some nuclear features are stored as covalent chemical modifications that survive dehydration and long-term storage, which we know, others exist only as spatial or biophysical relationships that collapse immediately upon cellular lysis. So once it dries, and once it, if it's not a fresh sample, and once it's dried and desiccated or whatever, dried out for the dried blood spot card, then what happens is you're hosed, right? So I put it has a stability of nuclear information under desiccation and how this breaks down. So it's all on the paper there. And we're going to stop here for today. So this is part 2, the NucleoGenesis project. We're going to move on to the next section, and we're just going to continue to go through this. But if you want to read it yourself, it's at syndicate-labs.io, NucleoGenesis, syndicate-labs.io, under NucleoGenesis. And you can read the whole paper there. And if you want to talk to me about it or just hit me up on socials. Otherwise, again, my name is Dr. James Utley, and I'll see you in the future. Peace.